This unit is all about solving, okay? And yesterday was a lot of just more of what we did in the previous unit. There was a little bit of an extra step and a few things to notice, but overall, I think pretty straightforward. But today we start something new based on something you did a little bit last year. But the trick is all these different ways that we solve in types of questions, we solve them in slightly different ways. And the trick for you is to keep them separate and knowing how to do which type. So today we're doing 1 day, we're doing 2 days of this. So this is the first day of solving polynomial inequalities. And so this is one of the types of solutions that we look at, one of the procedures that we look at in this unit. Okay, and it's very, very different from solving polynomial equations, although there are parts of it that are similar. But to get the final answer is very different from what you were doing yesterday. So again, you got to make sure you know this. If you didn't know how to do this and you tried to make it up yourself, I would guess what you would do and it would probably be wrong. We'll take a look at that after. What do you remember about inequalities from grade 11? Do you remember how to solve this? When we are solving an yes or no? I got no feedback on that. What do you think? Sort of. When we solve equations, we're finding the value of x that makes it true. If I was solving this as an equation, when does it equal 0? I move the 4 over, right? Everybody knows how to do this. And then divide both sides by 2. And 2 is the value that makes that statement true. But what does it mean to solve an inequality? So inequalities are different because it's not a single value that makes it true. So I'm going to start testing some values with this. Let's start with negative 10. Negative 10 times 2 is negative 20, minus 4 is negative 24. Is negative 24 less than 0? Yes. So I tried negative 10 for x and it worked. What about negative 9? That's negative 18 minus 4, that's negative 22. Is negative 22 less than 0? Yes, that also works. Okay, what about positive 10? 20 minus 4 is 16. Is that less than 0? No. So 10 is not in our solution set. Positive 10 does not work. What about positive 9? 18 minus 0 is 14. Not in our solution set. So like, I only tried a couple of numbers, but a couple worked. Negative 10, negative 9 worked. 9 and 10 did not work. So the threshold where we go from working to not working is somewhere between negative 9 and 9, right? But the difference with inequalities is there are many numbers that will make this true. So our solution looks a little bit different. So how do I do this? I do 2x less than 4. I just move the 4 over. It's the same. In this case, it's the same as solving a linear equation. Divide both sides by 2, and I get x less than 2. And that's the threshold where it goes from being not true to true. So anything smaller than 2 will work for this equation. Anything bigger than 2 won't. 2 times 3 is 6, minus 4 is positive 2, which is not less than 0, so that doesn't work. You have a question?
No.
You're going to tell me how to solve it?
Yeah.
That's what I thought. Okay. Does that make sense? We all remember doing this? Did you ever think of, or were you ever shown a graphical representation of this? I bet you weren't. Remember what I said yesterday about solving polynomial equations? You can always view it as like the left side and the right side and comparing two functions. What is 2x minus 4 in terms of a function? Hey, hit you with these random questions and you're like, I don't even really know what you're asking, but this is easy. It's grade 9. Just linear. It's just a straight line. So it's got a y-intercept of negative 4. And then a slope is 2, so up 2 over 1, up 2 over 1. And so if you wanted to sketch, you could just sketch and kind of just show the sort of intercepts. When is that less than 0? Like, isn't that blatantly obvious now what the answer to this is? Why x less than 2 is the answer to that question, because when is that graph, 2x minus 4, when is it less than 0? In other words, when is it below the x-axis? Isn't it so obvious what this means when you look at it as a graph? I don't think it's very complicated thinking about it algebraically either, but I think it's sad if we don't look at both. If we just look at the algebra and I just know how to solve, and there's a couple of quirky little rules for solving inequalities. You might remember those. If you don't, we're going to talk about them in a minute. But solving an inequality algebraically is relatively easy. But what does it mean? Well, it means if I sub any number less than 2, even 1.9 or 1.99, into that equation, it'll make it true. That's what it means. It means this is the range or the interval of values which makes that true. But graphically, it means something a little bit different, does it? Did you have another question or something? No. You good? Okay. So very interesting. That's what you did in grade 11. How would we do this? You might think to do that, but that's not going to help us actually. It's in the form that we want, so that's useful. Expanding it, what would that tell us?
Oh, yes. If I expand it, it just goes back to the thing.
Oh, yeah, if you expanded it and factored it, then that wouldn't be very helpful, yeah. What else? What do you think? What could we do? Adam? Nope. There's no x in there that I can factor out. Isaac, what do you think? This is what, don't write this down, this is what I would expect some people might think. So when is x minus 1 greater than or equal to 0? When's x plus 2 greater than or equal to 0? And when is x plus 3 greater than or equal to 0? Those are all different answers, though. X greater than or equal to 1, x greater than or equal to 2, x greater than or equal to -3, negative 2 and negative 3. So which one is it? If it's bigger than 1, it's already bigger than both of those. Is it all the numbers that satisfy all of these? In fact, this won't help us at all, and you'll see why in a few minutes. So this is maybe what your intuition tells you that you would do, but this is where what we did yesterday and what we're doing today separate, and we don't solve them the same way. This won't work. What do you think? What else do you think? We could graph it. You think that'd be helpful? Okay, and even if you're not sure if it would be helpful, it's always useful to graph and visualize these things. Adam, what do you think?
What I was going to say is pick the term that would be like the furthest to the right, and then like if it came back up.
But that's some good thinking, visualizing. Let's try this idea of graphing it. We're just going to sketch it, quick little sketch here. This has x-intercepts at -3, -2, and +1. What else do you know about this function? If I think of this thing on the side here as f at x. Lucas? Degree 3, thank you very much. What else? Thank you, positive leading coefficient. All the details we need in order to sketch. All three of those x-intercepts are straight pass-through. No turning points. Turning points, turns out, are really important in this matter, but we don't have any yet. So it's just going to kind of go like this. Now tell me, when is that expression greater than or equal to 0? And tell me it's not obvious. Isn't it obvious now when we're looking at this sketch? When is that greater than or equal to 0? Just like when we looked at the sketch of the linear equation. And if you're not quite with us yet, it's nothing more complicated than when is that graph above the x-axis? When is it bigger than 0? That's all it means. How easy was that? Yeah, no. Well, so yeah, how are we going to solve it? We have to actually write the solution. So, and go ahead.
Is the way we're gonna is the statement gonna look similar to like when we were saying when the sine graph is increasing? Or
Yes, very much the same way. But good connection. So this is kind of similar to increasing and decreasing. We're just going to write the intervals where it's true. So it starts below the x-axis. Again, we have to look at the sign here, right? Like we got to know what we're actually solving for. Greater than or equal to 0. So it's not greater than or equal to 0. Becomes greater than or equal to 0 at -3. So we start at -3. Dips back below the x-axis at -2. So less than or equal to x, less than or equal to -2. And then goes back above. And again, think about end behavior. Think about everything we did in the last unit and how useful it is all of a sudden. We know that end of the graph is going off into space. It's going off to infinity forever and ever and ever. It's never going to turn back around and come back down. So I can safely say when x is greater than or equal to +1. And there's, in this case, it has 2 intervals. But you can imagine it could have lots if it's a different degree and it goes back and forth above and below the x-axis. Imagine solving this with the sine graph. That was like, that would be pain. But anyway. Does that make sense, Isaac? Oh.
So why is it greater than or equal to the x-axis?
Because that's 0.
But isn't also 0?
But that's when x is 0. We're wondering when this function is 0. And if I think of this function as y equals that, then it's when y is 0, which is x intercepts. Yep. Any other questions? I thought I saw somebody else with a hand up.
Wait, so can we do it without the sketch?
There is one other way. We're going to see that a little bit that you can do it, but the sketch is probably the easiest. Okay. And yeah, if you weren't with us, this is how we're doing it. Like you draw a little sketch and you read your solution from the sketch. What if it wasn't in factored form? Put it in factored form. That's tomorrow's lesson. Which you already know how to do, so it's not that big of a deal, but we'll see a few different little quirks and things that arise. All right, let's do another one. What do you notice about this one? Has a negative. Very good. That's going to be pretty relevant. You'll see why in a little bit. What else do you notice? Very good. It's degree 4. What else? Anything else? It says less than 0 instead of greater than or equal to 0. It doesn't include. It's not equal to. It's just less than. Like those are some of the little details when you're solving inequalities that you do have to absolutely think about. Okay. Anybody notice anything else?
When there's no equals to, so it's
Yeah. Good. Adam?
There's going to be like 3 answers, I think.
Okay, interesting. So there's not always 2. There could be 3. There could be 1. There could be none, actually, right? It's possible. Maybe not in this case, but in some cases. Anything else? What's this mean? That little 2. Turning point. That's going to be important. I mentioned that turning points in this are very important to notice, and they can be tricky in terms of interpreting our solution. So we're going to see an example of that. So it's degree 4. They either both point up or both point down. Is negative leading coefficient. So they're both going to point down. So I'm going to go to -4, -1, +3. And I'm going to go like this. Straight pass through. Whoops. Kind of missed there. Straight. Let me fix it. Turning point, you can watch me do it again. Straight pass through, straight pass through. When is this graph less than 0? Adam?
At like less than at where 3 is, and then where it touches the graph, what you say?
Good question. If this was less than or equal to, then it's true. Then it would be true all the way up to there, right? It's below or touching the x-axis everywhere there and here. But it doesn't say equal to. So Isaac, what do you think?
X is less than 3.
Not less than 3. Let's start at the left side. It's going to be x less than -4. I can't include 4, so I have to just skip over 4 because it's equal there, and we're not including that, just based on that. So then I also have -4 less than x less than -1 because it's below the graph there. So it's below the graph here, it's below here, but not at that point. And then it's above here and it's below here. So then I include that one. X greater than 3. X is greater than 3. The graph is below, but x is bigger than 3. And if you need to, you can sub values of x in and check that. Sub 10 in and see what you get. So this one had 3 intervals where it's true. If I subbed -4 in, I'd get 0. So 0 is not less than 0. 0 is equal to 0. So that wouldn't satisfy this inequality, would it? Isaac, you're not happy about something? We're just asking when is this graph below 0? And for 3, it'll be down here. For 4, it'll be down here. For 5, it'll be down here. For 6, it'll be down here. For all those values. If I go out to x equals 6, it'll be right around here. Where is my graph going to be? It's going to be down there somewhere. So for 3 and bigger, the graph is below 0. Yesterday I talked about how when you're doing an equation, you can divide that number there out and get rid of it. Remember that? What happens when we divide by a negative with inequalities? Who remembers that from grade 11? Nobody, really? Yeah, don't you have to flip the sign? Do you remember that? Multiplying by a negative or dividing by a negative, you have to flip the sign. Vaguely, okay, well, if you don't remember, you do have to do that. Let's see what that looks like in this case. Okay, so I'm going to come over here, and I'm going to divide both sides by -2. And I'm going to sketch it. How is this graph going to change? Now it's got a positive leading coefficient. But the x-intercepts and stuff didn't change, so I still got -4, -1, and 3. But in this case, it's going to start up here, turning point. So if I want my solutions to be the same, don't I have to flip the sign? Because we flipped the graph. So now I want to say when this is bigger than 0, right? And now we get the same solutions. So that's how you do it. You take the graph, you do a quick sketch, and you read your solution from the sketch. You got to know how to write those intervals out properly. But that's about it. We're going to do one more example. But any questions? I'll show you the other way that you could solve these. And the only reason I'm going to show you this is because it is a technique that we use in mathematics. And in some cases we have to. In this case, we kind of have a better way because I think the sketch is a better way. But you could solve all of these the way that we're about to do this one. It's not really that much more work. It's kind of similar in some ways. And if you like it better, you go ahead and do it. That would be fine. And like I say, in some other aspects, definitely in calculus, we do this kind of stuff again. And we'll see it a little bit in this course as well. So, and it's a technique that we use, so it's interesting to see, I think. And instead of drawing a sketch, a full sketch, we just draw a number line. Okay? And I label the, you could think of them as like the x-intercepts on the line. So I've got -5. I've got -2, 0, and +3. Right? And I'm just going to test those intervals. So I pick a number, because inside that interval, it's not going to change. If it's above 0, it's going to stay above 0. If it's below 0, it's going to stay below 0. Think about the graph, and we already understand that. So if I test any value in that interval and figure out where the graph is, then that'll be good. So I'm going to start with -10. And I'm just going to plug it in. If I put -10 in for x, -10 will be positive. -10 plus 5 is negative. I don't care exactly what it is. I just care that it's negative. -10, because I'm imagining like putting -10 in for x to see what I would get. -10 plus 2 is negative. -10 minus 3 is negative. If I multiply 3 negatives together, my result will be negative. So it'll be negative in that interval. Now I pick something between -5 and -2. What's a number between -5 and -2? -3. So -3 is positive. -3 plus 5 is positive. -3 plus 2 is negative. -3 minus 3 is negative. 2 negatives make, say, something between 2 and -2 and 0, so -1. So that's positive, positive. -1 plus 2 is positive, and then negative. So that's going to be negative. Pick something between 0 and 3. How about 1? So that's going to be negative. 1 plus 5 is positive. 1 plus 2 is positive. 1 minus 3 is negative. 2 negatives makes positive. And the last one, I'll pick a big number, 10. This is negative. This is positive. 10 plus 2 is positive. 10 minus 3 is positive. 1 negative means negative. And it's the same if I did it this way, because it would start, it's degree 4, and it's all straight pass-throughs. So I can see where it's negative from this little number line or from the graph they match up. And we always have to go ahead and state our solution. So when is this greater than 0? Between -5 and -2, and between 0 and 3. The only places that it's greater than 0, the only places that it's positive.